Hello everyone, my name is Memory Kulanga. In this presentation, I will explain two questions from the metallography and heat treatment. The first question that I will address is one, explain the basic principle of the Grossmann test and in determining the hardenability of steel, and also explain the terms D0, DI, and H. And number two is explain the stages of annealing process along with the relationship between the mechanical properties, that is tensile strength, ductility, and microstructural evolution at each stage of the annealing process. The basic concept of the Grossmann test is the purpose of this test is to measure the hardenability, which means how deep steel can harden when it is quenched. This is different from the hardness test because hardness tells us how hard the surface is, while hardenability tells us how deep that hardness goes inside the material. The basic principle of the Grossmann test is quite simple. So we take several cylindrical steel bars with different diameters. We heat them until they become austenite and then cool them rapidly using a quenching medium like water or oil. After that, we cut the bars and examine the structure from the surface to the center. So because the cooling is faster at the surface and slower at the center, the structure will gradually change from martensite near the surface to the perlite or bainite towards the center. We then identify the bar where the center contains 50% martensite. This condition is important because it represents the limit of effective hardening. We have three key terms in the Grossmann test. The first one is D naught, which is the critical diameter. We can say it is the real condition diameter. The definition of the critical diameter is that it is the diameter of a steel bar that produces 50% martensite at the center. It is measured under specific quenching condition. Then the key idea of the denote is it tells us what actually happens in practice. And then it depends on steel composition and quenching medium. If it is oil, whereby we have a slower cooling, we have a smaller denote. And then if we're using water as the quenching medium, it means the cooling is very faster. It's faster than when we're using oil, so the denote will be larger. And then if the denote is small, it means hardening doesn't penetrate deeply. And then if the denote is large, it means hardening penetrates deeper. And then number two is the ideal critical diameter, which is Di. So this can be said it's a material property. The definition of the Di is it is the diameter that would give 50% martensite at the center under ideal quenching conditions, whereby we have extremely fast cooling and the edge is close to infinity. The key idea that the ideal critical diameter gives us is it represents the intrinsic hardenability of the steel, and then it depends only on chemical composition and it is not affected by the quenching medium. And then number three is the H, which is the severity uh, quench. So the third term, which is H, it represents the severity of the quenching. So it tells us how fast the cooling happens. Lower H, it means the cooling was very slow. Then if H is high, it means the cooling was quite faster. So oil has a lower H and water has a high H. So as H increases, the steel hardens deeper. Then now we're going to explain the stages of annealing and its effect, the stages of annealing and then how it relates with the mechanical properties. So annealing is the heat treatment process used to reverse the effects of cold working by heating the material and we cool it under controlled conditions. Then this process occurs in three distinct stages, and that is recovery, recrystallization, and grain growth. So it happens in a sequence: recovery first, and then recrystallization, and then grain growth. And then recovery It occurs during heating at elevated temperatures but below the recrystallization temperature. At this stage, the dislocations reconfigure due to diffusion and relieve the lattice strain energy. The electrical and the thermal properties are recovered to their pre-cold work state, but the mechanical properties they are not recovered yet. And then what happens is we heat, and then there is increased diffusion, which cause enhanced dislocation motion, and then that will decrease the dislocation density by annihilation process, and then we form lower energy dislocation configuration, and then we relieve the internal strain energy of the grains. And then the second stage is the recrystallization temperature. Recrystallization stage, sorry. So it is the formation of new strain-free equix grains, and then the recrystallization it occurs when the material has undergone a certain amount of deformation. So the driving force is deformation. If there was no deformation that had occurred on a material, then recrystallization won't occur. And then the grains here they will contain low dislocation density equivalent to the pre-cold work condition, and then the rate of recrystallization it increases with the amount of cold work. And then we have what is called recrystallization temperature. This is the temperature whereby the recrystallization process will complete in 1 hour. And then recrystallization temperature, typically for a metal, it will be one third or half of the melting temperature, or in some metals, it's 0.7 TM in some alloys. And then the third one is the grain growth. So this is whereby we have a growth of new grains will continue to grow at high temperatures, and then it does not require recovery or recrystallization. So this means if our material here was not deformed, if we apply heat, its grains will grow, and then it occurs both in metals and ceramics at elevated temperatures. It involves the migration of the grain boundaries, and then the large grains they will grow at the expense of the smaller grains, and then with the process called grain cannibalism. And then the reduction of grain boundary area is the driving force. So, and then in this grain growth stage, it also uh, in the grain growth there is also reduction of the grain boundaries. And then now we learn about the how the mechanical properties. So in the recovery stage, we can see that the ductility and the strength and the hardness they don't change significantly, as I've already mentioned. And in the recrystallization, we can see there is a significant increase of the ductility, while the strength and the hardness they decrease. And then in the grain growth, because there is a reduction in the grain boundaries, we can see the strength reduces, and then the ductility it continues to be increasing but remains a bit constant. Thank you for listening. This is the end of my presentation.